Hey, I never know when it starts. Good afternoon, early evening, yes, to you. We are going to take a look at thermochemical equations, okay? Let's go ahead and get started. We'll be reflecting or using several of those practice problems that I attached this video in Google Classroom. Very simple topic we have here. Nothing too in depth. All right, so what we have, again, guys, is thermochemical equations, all right? This is basically a chemical equation with a delta H attached, right? So therefore, it shows the energy change of the process. Okay, let's look at some examples. A thermochemical equation is going to look something as such. You're going to have your balanced chemical equation, right? Oh, here's your balanced chemical equation. And they're going to have an enthalpy change to it. So it may look like that. Notice that the over here, heat, right? This is your energy. Energy is a product, right? Therefore, this is exothermic. If it was written in the reverse direction, it would be reactant and it would be endothermic. Okay? Now, I could do this in a few different ways. Let me go back to my notes. I could do, let's write that one. That was, what was the mole? 2 octanes, 25 oxygens. 2 octanes plus 25 oxygens yielded 16 carbon dioxide plus 18 H2Os. And that had a delta H of, I'm going to write it right here, 10,148 kilojoules. Right? So the fact, however, guys, I could write delta H is equal to the negative 10,148 kilojoules, or, right, I could write 2C8H18 octane plus 25 oxygens yields 16 carbon dioxides plus 18 H2Os plus 10,148 kilojoules, right? Now, if I reverse this reaction, then it is no longer exothermic, but is now endothermic, all right? Let's make that look a little bit better. Right, but is now an endothermic process, right? It's just the reverse. If it releases energy in one direction, then it would absorb an energy in the other direction. It's easy to understand. So let's write the same reaction in the reverse, where the products become the reactants. And we would have to add 10,148 kilojoules in order to actually make this process. Oops, I need to make the reactants, the products, in order to make this process actually occur. Right? So we have an endothermic process, or I could write this as 16 CO2 plus 18 H2O yields 2C8H18 plus 2502. This time my delta H would be equal to positive 10,148 kilojoules. Okay? So what that means is when this reaction goes in this direction, you must add this much energy in order to make this process occur. Okay? Or the delta H is this, notice it is positive, meaning energy is a reactant. Positive, therefore, energy a reactant. And then over here, the reverse of the process in this direction has a delta H, which is negative, so that we see that the energy is a product, right? So here we have energy released, therefore delta H is negative. You gotta pay close attention to those signs, okay? Now we can look here at a couple examples. Consider the following thermochemical equation for kerosene. Once again, heat, a product, therefore exothermic. All right. When 21.3 grams of carbon dioxide are made, how much heat is released? Well, what this tells me is what my equation tells me. Anyway, hold on. They give me 21.3 grams. They ask me about the heat. Well, this equation tells me that when 24 moles of carbon dioxide are produced, this much heat is released. So I will need to get my grams of carbon dioxide to moles of carbon dioxide. And now I can use my thermochemical equation because it tells me this is like another product, right? It tells me that when 24 moles of carbon dioxide are produced, we have a whopping 15,026 kilojoules of heat released. So the question is how much heat is released? So we just need to throw some numbers into our calculator, right? We've got 21.3 times 15,026 equals divided by 44.01 equals divided by 24. I forgot to put the parentheses, so I'll just divide by both. Oh, and it looks like I've got a 303 kilojoules released. Okay, let's do another one. If 500 kilojoules are released by the reaction, how many grams of, what is this called? I'm not sure. Kerosene must have been consumed. Well, you know, we have to start with what we have, right? I know that kilojoules has to go here, and my kilojoules is going to come, let me clean up my equation. My kilojoules is going to come from my thermochemical equation right here. And I'm going to relate that, right, kilojoules to grams of C12H6. I'm going to relate that to this. So I'm going to do kilojoules to moles of C12H26. And I'm going to use my balanced chemical equation. There are 2 moles of kerosene for every 15,026 kilojoules of heat produced. We only need to produce 500 kilojoules, so we don't need 2 moles. We need about a third of that. And we see that 1 mole, we need it in grams, however, so we will have to convert this to grams. Let's do the mass of carbon, 12.01 times 12, plus our 26 hydrogens times 1.01, close parentheses. Wow, 170.38. I will now multiply that by 2, and I will multiply that by 500. And I will divide it by 15,026. And I've got 11.3 grams. Grams of what? Kerosene. Would be needed to be burned. Not very much. Not very much indeed. If this reaction, this kerosene reaction, were being used to generate heat, how many grams of kerosene would have to be reacted to generate enough heat to raise the temperature of 750 grams of water from 10 to 90 degrees? Oh, well, I need to get the heat required to raise the temperature of 750 grams, right? Let me specify. If I get Q equals MC delta T, and that is the heat required, right? So that's 750 grams of water. Water has a specific heat of 4.184 joules per gram degrees Celsius, and we need to raise the temperature 90 minus 10, 80 degrees Celsius. So how much heat do we need to do that? Well, we need a lot of heat. We need 2.5 times 10. Let's do 2.5. 1 times 10 to the 5th joules of heat is needed. And the question is, how many grams of kerosene would need to be burned? So let's start with what we now know, 2.51 times 10 to the 5th kilojoules. We will need to convert our kilojoules to joules. 1 is 1,000. No, I don't need joules because my enthalpy up there, my energy, is already in kilojoules, right? My bad. If you look right here, it is in kilojoules. What was I thinking? There are 15,026 kilojoules for every 2 moles of kerosene, but we need the grams. We've already calculated the molar mass. It's right up above. It is 170.38. So 170.38 times 2 times 2.51 with an exponent of 5 equals, divided by 15,026 equals. That looks like we're going to need 5,692 grams of kerosene. I have not watched my significant figures. And I'm going to just be okay with that right now. Okay? That's a lot. Like 500 kilojoules, no big deal. 200,000 kilojoules, that requires a whole lot more, right? Okay. Let's look at our next reaction. I've got sodium nitrate reacting with sulfuric acid, sodium hydrogen sulfate, nitric acid. This time our delta H is written in this form. It is positive. Therefore, this is endothermic. And in order for this reaction to occur, heat goes into the system. How much heat must be absorbed by the reaction system to convert 100 grams of sodium nitrate into NHSO4? Okay, well, if 100 grams of sodium nitrate is reacting, and I want to use my thermochemical equation, I will have to convert those grams to moles, right? So sodium is 22.99 plus nitrogen 14.01 plus our 3 oxygens, each at 16 apiece, 85.00 for every 1 mole. Now look at your equation. 1 mole of sodium nitrate requires 21.2 kilojoules. All right, 21.2 times 100 equals, divided by 85 equals 24.9 kilojoules absorbed. I always ask myself, does that make sense? And it does, because 85 grams produces 21, so, or needs 21. So 100 grams needs a little bit more heat. All right. One more. What is the enthalpy change? We're not going to do this one because you guys don't know how to do these molarities yet. So we won't do that right now. Okay. I think you can, if you've got stoichiometry, it's just the enthalpy value literally becomes a stoichiometry participant, if that makes sense. Right on.